So this is the last bit of our unit for HLs, okay, the central limit theorem. And it's actually just kind of something that we're adding on to the end of what we've already done, right? We've already looked at normal distributions and Poisson distributions and all these other things, but all of these distributions tell us the probability of getting a specific value when I take out one single object from my sample, right? From my population. Okay, it just shows one object. Okay, now what we're going to do, we learned earlier this year when we did statistics that sometimes we wanted to take do several trials in a sample, right? We could have a sample size that is larger than one. The bigger our sample size, the better the data that we can get. All right. So the central limit theorem kind of takes this into account, the fact that we're going to take more than one sample out. Now, we have talked about for a specific probability, we can use a binomial distribution if we want that to use that probability over and over and over again for, multiple trials. But this is kind of a more general theorem, and we're going to talk about it right now. Okay, you can see it here on the screen. It says the mean of a sample size n taken from any population with mean mu and standard deviation sigma can be modeled by a normal distribution with mean mu and standard deviation sigma over square root of n, provided that n is at least 30. Okay, so what this is saying is that if I take n is at least 30, so if I take a large sample, right, I take lots of data points, at least 30, and I'm drawing these out of my distribution, that no matter what type of distribution it is, doesn't matter what type of distribution, it can be binomial, it can be Poisson, it can be a normal distribution, it can be one of those other types of distributions that we didn't even talk about. Regardless of what type of distribution it is, when I take those samples out and I look at that sample, the average of my sample is going to be mu, which makes sense. The average should match up with the average. Okay. Now, the standard deviation of my sample will have a standard deviation of the standard deviation, the original one, the one of the population, divided by square root of n. Because this standard deviation is when I'm taking one sample, right? It's what's the standard deviation of a single object. But when I start to take more samples, my standard deviation is going to decrease because there's actually going to be less spread the more data I take, the more certain I'm going to be in my results. All right? There are mathematical proofs for this, but they aren't necessary for this class. And so I'm not going to take time to go into it because I don't think that it's necessarily valuable to us right now. What I do want to do is go through one example so that you can see how this type, how the central limit theorem can be used within a question. All right, so let's go ahead and we'll move on to the next page. Remember that the whole idea of this is that no matter what type of distribution our original population has, it doesn't matter that when we take all of those samples, that the samples will have a normal distribution that has mean mu and this new standard deviation. All right, that's the key, is that the sample, when we take it, that will have those qualities. Definitely a normal distribution. Does not depend on what type of function it is, what type of distribution. All right, so let's look at this question right here. The number of emergency calls per hour to a hospital between 9:30 a.m. and 10:30 a.m. each day follows a Poisson distribution with parameter 6.3. Use the central limit theorem, all right, central limit theorem, to find the probability that in 40 days, notice that the number of days is more than 30, the mean of the number of calls between 9:30 a.m. and 10:30 a.m. is less than 5.4. Okay, now notice that this is a Poisson distribution. Okay, that is not important to the question. Okay, well, I mean, it is important, but that's not important when I look at the central limit theorem. Central limit theorem works for any type of distribution. All right, now there really is no other way to do this, right? It's not like the other ones where it's asking for what is the probability that I'm going to have half of the days be under 5.4, right? In that case, I could use the Poisson CDF, get a probability, then use the binomial CDF to find out getting, half or more of the days being less than 5.4. Unfortunately, it's asking for what the total probability is that I'm going to get an average less than 5.4. Okay, so what we're going to do is we're going to create a new distribution for what those 40 days should look like. All right, so we're going to go ahead and use the central limit theorem. The central limit theorem says that the mean of the sample is going to be equal to the mean of the original population. Now, the mean of the original population was 6.3. And so, therefore, the mean of my sample of 40 days will be 6.3. Okay? Assuming central limit theorem is true. Okay? Next, we get the standard deviation of the sample. Okay? And the central limit theorem says that the standard deviation of the sample is equal to the standard deviation of the population divided by the square root of the number of trials. And in this case, we have that 6.3, remember 6.3, the parameter of Poisson, is the variance. And so the square root of 6.3 is our standard deviation. And then on the bottom, I need square root of 40, because that is the number of trials that we're going to take. And if we punch this into our calculator, then we will get the new standard deviation. And so I'm going to punch that into mine real quick. So I'm going to go square root of 6.3 divided by square root of 40. And I get 0.397 as my standard deviation. All right. So now that I have that, I can put that in. I now have, remember, central limit theorem says that this is going to be a normal distribution. Okay, so now I have a sample of 40 days. A sample of 40 days will have an average of 6.3 and a standard deviation of 0.397. And so because of that, we can now put it into a normal distribution. And we can say that the normal distribution is going to have 6.3 as the mean, and then it's going to have 0.397. Remember, this is variance in our notation. Okay, and so we can find out now what is the probability that this function, whatever it is, let's just call it big X for our sample. What's the probability that this number, the average for this number, is less than 5.4? Okay, and we are talking about the average here, right? Because that's what this is. This is the mean, and this is the standard deviation of the average as a normal distribution. So we go ahead and we can put this in to our calculator as norm CDF. Remember, with normal CDF, they do ask us to put in our range first. So go ahead and put in our range. We'll go from negative 9E99 or some other really big negative number. We'll go up to 5.4. We'll give it its average of 6.3 and the standard deviation of 0.397, or you can copy and paste that number from the previous step. And when we get our answer, we should get that the probability is 0.0117. All right. Now, why do we care? Okay, this is a question that should always apply to what we're doing with our applications questions. Why do we care? Okay, well, let's say that we took measurements for 40 days, and after 40 days, I got an average that was less than 5.4. What is the likelihood of that? What is the likelihood of me actually taking samples for 40 days and getting an average less than 5.4? Well, it's about 1%. It is very unlikely. Is it possible? Yes, but it's very unlikely that if the average is 6.3, it's very unlikely that the average over 40 days will be less than 5.4. If I'm getting that number, then it's probably worth double checking. it's probably worth going back through, how did I get this 6.3? I mean, did somebody make it up? Did somebody just kind of throw it out? Or is this 6.3 based off of real data? Is that real data based off of data that is up to date? Or is it old, before, they opened up a new hospital? Or, that then starts to ask questions. If something happens that is very unlikely, then, that's a chance that we say, okay, well, let's look into this further. Let's dig in a little bit deeper, take some more tests, test it again, and find out if these values really are what we've been told they are. Okay, and this works for anything. You could do it for polls at any type of poll, any type of survey. If you get certain results and the results are very low probability, it doesn't mean it's wrong. It just means that it is unlikely. All right. So anyway, hopefully that makes sense. Use this to do a couple of problems tonight. I'll show you a couple from the book where you might be able to use this, and then hopefully you'll be prepared for your celebration.